closed strings, and we're going to repeat exactly the same words. Any questions for here?
Is it any value pass of tau?
Yes. All this simply tells you that, so this is at tau equals 0, it's a closed string. This is at tau equals 1. So you choose your origin sigma equals 0 to be here, and now at tau equals 1, you decide to choose the origin on the circle in an independent way.
Doesn't it have to be multiples of tau?
Sorry?
Doesn't it have to be multiples of tau?
No, it has nothing to. Well, yeah. Okay, so I'm assuming that so that is all more there. Right? So all this relation is you're right. So all this relation is more there. But the point I'm making is that there is an independent way of choosing the origin, and that's actually very crucial in order to get the right graviton. Alright guys, so I told you, and you believed me, that there's going to be the expansion. You have to believe me more. There will be the same equation of motion. That's easy to believe. C squared delta sigma xi. And so that's actually a solution there. Now, independent degrees of freedom. So independent degrees of freedom. So now we have twice as many oscillators. And then I have center of mass. And then I have x minus and x plus and p plus. Now, there is something that I cannot understand, and maybe if somebody can explain me, I would be very grateful. So I'm going to make a statement, and then that statement, it's a convention. So it's not, it's just a name, but I cannot understand why it's named this way. So this thing is called the left-moving wave. So if we look at the mode expansion, so there is a standard in a moving wave. There is sigma minus speed times tau dependence, sigma plus c times tau dependence. Those are the standard, moving wave type of expansion. So this wave is called left moving wave, which is important because when I will be referring to a left moving oscillator, I will keep in mind those Fourier coefficients. Fourier coefficients that enter here, and so this one is called right moving wave. Now, why am I saying that I don't understand this? Because that's counterintuitive, right? So actually, if I look at this wave and I ask in which direction this wave is moving, so this wave is actually moving to the right. I'm sorry, because see what's happening is that if I have a wave here, so if I have a top of a wave somewhere here, and as the time goes forward, right? So so the top, so I have sigma here, so sigma top. So sigma top will move to the right. So from this perspective, I would say that wave is the right moving wave, and the other one is the left moving wave. But modular this uncertainty, which took me when I was in your stage, really agonizing hours, I couldn't understand. I don't understand its things. So anyway, so there is a sum of left-moving oscillators, right-moving oscillators. So those are left, and this is right. So again, you can think of that the string theory convention that the axis is the axis. Okay, good. So those are degrees of freedom, and then we have commutation relations. So when we do canonical quantization, so we'll have this guy, and we have central of mass. So then the left-moving and right-moving oscillators are completely independent, so they satisfy independent oscillator algebras. Alpha Jn equals m, delta ij, delta n, and it's the same as it will be. Right, so everything goes as before. So I can go ahead and again compute the Hamiltonian, express the Hamiltonian in terms of these oscillators. And there is some heuristic argument why the answer is the way it is, but I'm not gonna, because I want to finish today everything about light cone, so I'm just gonna write down the answer, because for some of you, heuristic answers won't be sufficient anyway. So what we will find out here, that the spectrum of the closed string will take the following form. So I will have 2 over alpha prime. So here I have n plus n tilde, sorry, that's a plus a tilde. So the tildes correspond to right movers. So the situation really parallels open string. The only difference is this factor of 2, which you can sort out if you carefully follow the normalization. So n and tilde divides in the same way as for the open string, 2 minus 2. Sum n equal 1 to infinity, and comma I. So those are occupation numbers in the left moving sector. And then I have an occupation. So these are eigenvalues of the operator minus n I alpha I. And then here I have 1 e minus 2 sum n equals 1 to infinity and tilde, and those guys are just their eigenvalues of right moving oscillators. Okay. So it is a natural generalization, right? So we have independent left and right moving, so each of them will come with its own occupation numbers. They will add together, and then there will be an ordering constant. There will be 2 of them. But you might have imagined that in the discussion of these constants, nothing will really change, because again, that will come from. We will do it in exactly the same way how we did for a simple harmonic oscillator, which means that we're going to use exactly the same values for those constants. 2 minus e divided by 24. Okay, so far everything just repeats the open string. So as I said, there was a subtlety. There was a subtlety associated with the origin of a circle. And so what I'm going to show you now, that this subtlety imposes the following conditions. So here, little left movers and right movers can be completely arbitrary. Okay, there is no, I can excite 3 left moving oscillators and 1 right moving oscillator. However, what we will see is that requirement that the theory is invariant under this symmetry, which is a symmetry of closed strings, right? So this is a hidden symmetry that we kind of forget when we discussed closed strings before. So this requires that there is a constraint, in some sense global constraint, on left moving and right moving oscillators. So that's not very strong constraint, right? So this simply tells that all the total level on the left must be equal to the total level on the right, which simply means that those sums must be equal. It doesn't say necessarily that you must excite the same, exactly the same type of oscillators, only that this condition must be true. So this condition is known in string theory as level matching. And so you will see that when we will discuss what is the spectrum of excitation? Obviously, it will put a constraint. Some of the excitations will not be allowed because they will violate matching. So what I want to do now is to show you that this symmetry actually leads to this requirement. Okay? So let's go ahead and let's see that. So what I'm going to do, the idea is we're going to construct a generator associated to infinitesimal translations on a circle and generator associated. Associated with sigma goes to sigma plus S of tau. And then, how am I going to call this generator? Let me call this generator, I don't know, Q. And so what we will require that, that when Q acts on a physical state of the string, so it must vanish, right? So that would guarantee that the physical states are invariant under this symmetry. Okay. So how do we construct this? How do we construct this operator? And I just want to go into more details here. One of the reasons is because Joe omitted this in his book. So I'm going to discuss this. So let me go to a Lagrangian description. So I'm just going to write down the Lagrangian that we derived before. It's like h x minus plus 1 over 4 pi alpha prime, an integral from 0 to L d sigma delta xi psi one sigma xi. So I'm using the Noether method to construct the conserved quantities associated with certain symmetries, and so that's kind of a nice review of this method. So what we're doing, we're looking at shift. So if I have an infinitesimal shift, right? So now it's infinitesimal, so I'll put absolute. So if I make this shift here, so my coordinates x of I, remember that they depend on tau and sigma, so they will go to x of I plus delta x of I, and delta x of I is just going to be absolute L sigma of x of I. Right? So that's an infinitesimal transformation of the fields. So once the fields get transformed, my Lagrangian will also get transformed. And because what we are doing, we're doing asymmetry transformations, this thing must vanish on shell. Right? So which leads pretty much to that condition that an operator associated with this transformation that will give us the operator Q when acted on a physical state must annihilate. Okay, so let's compute delta L. It's a very straightforward computation. So the only change here is the shift of x of I. X minus is not being shifted at all because it doesn't depend on sigma, it depends on tau. And so you can see that the only contributions come from here. So I'm just going to write it down and you tell me if you disagree. Well, there are two x's everywhere, so there will be a factor of 2. So I have 2 over 4 pi alpha prime. And then I have an integral from 0 to L, d sigma, gamma sigma sigma. And then and here I have del tau xi, del 2 tau sigma xi times epsilon. Okay, so this del 2 acts only on xi, it doesn't act on epsilon. And then I have plus gamma sigma sigma del tau xi del tau epsilon del sigma of xi. So that will come from the first term, and from there will be two contributions because I can differentiate either epsilon or x. Now, remember that our epsilon depends only on tau, doesn't depend on sigma, right? And so what happens is that from the second term, there will be only one contribution. I have del sigma xi, del 2 sigma xi times epsilon. Great, so very good. So what I'm going to show now, I'm going to show that this guy is equal to 0. So that's the first thing I'm going to show. And then I'm going to show that this guy is 0 as well. And so we will be left with only one piece. So why that thing is 0? Okay, so let's look in some details. So from 0 to L, I have a contribution to sigma, gamma sigma sigma times epsilon times del tau xi del 2 tau sigma of xi. Right? So first of all, recall that we are in a Lycombe gauge, so those guys does not depend on sigma, so I can write it down in this way. And then I have an integral. I have an integral from 0 to L d sigma. And so, so you can see that I have a sigma derivative here, but so this guy I take out, I have two x's here. I can write down whatever is left as 1/2 del sigma del tau of xi del of xi. Okay? So what I did, I actually just effect of 1/2 because sigma derivative can act on either of the axes, and so that will give you exactly this term up here. But now what you see is that what I have here is a total derivative, and because of the periodic boundary condition, it will seem to vanish. Okay? So this is a total derivative, and with periodic boundary condition, it vanishes. So actually, exactly the same argument goes for the second term. So the second term gives gamma sigma sigma minus 1 times epsilon. And then I have from 0 to L d sigma. And then I have del sigma of well, 1/2 again, del sigma of xi, del sigma of xi. Right? Exactly the same manipulation. And so again, because of the periodic boundary condition, that integral vanishes. So what we are concluding that upon infinitesimal variations associated with that shift, so the Lagrangian transform in a simple manner. Our delta L is 1 over 2 pi alpha prime, and I have z to L is sigma del tau So, well, actually, so this is a variation of the Lagrangian, but actually we have to talk about the variation of the particle action. Okay? And that's an additional integral. There is an additional integral with respect to tau. So this is the tau delta L. Okay? And so you can see what I have to do now. I have to integrate by parts. So I can integrate by parts, and so I can write this down as an integral, right? Of d tau absolute L tau times q, where q is the following quantity. So q equals to minus 1 over 2 pi alpha prime. And del tau of xi, sigma of xi. And then I have integral from 0 to L to sigma times. Okay. So is it clear? Okay. So again, so what we are showing that the variation of the particle action is given by absolute times something, and since it must vanish, so this must be equal to 0. So our operator Q is a conserved quantity which is associated with this infinitesimal translations. So Q is a conserved quantity. And so it's given by this explicit expression. I can go one step further and write it down. So this term here is proportional to the momentum density on the string, ball-shaped momentum density piece of I. So this is 2 pi alpha, and then I have an integral from 0 to L, d sigma, d sub I, del sigma of x sub I. So this is very simple, expression for this operator Q. So now, what we can do, we can actually substitute the mode expansion, right, and evaluate what that Q is in terms of our creation and manipulation operators. Find out Q equals minus 2 pi divided by L. So here I have summation n equal 1 to infinity. Here I have pi. Okay, so there is this very nice expression. Now, now our normal ordering constants a and a tildes are exactly the same. So this combination will vanish, and so this infinite sum is simply the total left moving level, and so this combination here is a total right moving level. And so our operator Q is equal minus 2 pi divided by L and minus n total. So as I promised you, the symmetry associated with the choice of the origin of the circle leads to the condition that the levels of left moving and right moving excitations must be matched. All right, guys, so any questions? Good. So, let's see what spectrum we will get for the closed strings. So we have a nice formula somewhere. Write down again formula. So m squared is q time and plus filter and then plus q minus d divided by 12. Okay, so here I just substitute these values in a filter, and we have one condition that n must be equal to n filter.
Yeah. Sorry, related question.
Yep.
You're assuming that n is equal to n tilde, but all we really showed was that time period of q is equal to 0, not necessarily.
Which means that it is conserved, right?
Right. So n minus n tilde is constant.
Well, no. See the way. Right. So this is the generator. This is the way how we use Nernst's theorem in order to construct the operators that act on your Hilbert space associated with certain symmetry transformations. Okay. So in other words, if I act, so the idea is the following. So if I have some state, some physical state, I don't know how to call it, but yeah. And so if I'm going to act with this infinitesimal rotations, then my state n will go to n plus epsilon times q. Okay. So that's a transformation on the what will look like on the Fox states. And so in order for our physical states to be invariant under these transformations, Q must be annihilated by n.
So does that mean when you act on a physical state with Q, that brings back the level matching condition as equal n tilde?
Right. So I guess maybe that's related to kind of initial conditions. So we have to assume the vacuum, whether it's so the vacuum is being annihilated by this Q operator. Right.
Okay.
So if you wish that's yeah, right. So that's probably the right way of thinking.
So we start out with n equals n tilde, it will always be.
Or more like saying, again, we're talking about the states, right, the physical state. So what would the right thing to say is that we start with the ground state, and we're going to assume that our ground state is invariant under this transformation, right? So remember the ground state will be 0, 0, and then I have k plus and k up, much like in the open string. So those are left moving and right moving oscillators. So I'm not going to act with any raising operators, right? So that's my ground state. And so if you wish that we're making an assumption that our ground state is being annihilated by Q. Okay. And so then once we start building up the cyclic state, we must have level matching. Which is also, this is an obvious statement, by the way, because the ground state has zero number of zero level, right? So the n acted on the ground state is 0, so I don't have to make actually even this assumption. right? So I'm just saying, and this is an operator which is insignificant itself. But when it acts on the ground state, it's 0.
But I do not think you are going to convince.
Convince you in what? No, no, it's okay.
I do not think it's convince me.
So,
For example, if you talk about the momentum,
yes.
okay, when momentum operator acts
Yes.
on the state,
Yes.
it's not vanish. It's a conserved quantity, but it does not vanish.
Well, it will. No, if your state is an eigenstate, right? So it will. You have exactly the same state. It doesn't rotate your state. So what I'm saying here, I'm saying how does my state rotated in a Hilbert space? If I act with this infinitesimal transformation, right? So my the states in my Fock space, they are not eigenstates of this operator Q. So in general, they can be rotated. And so what I'm saying that if so the ground state is invariant, is naturally invariant under these Q transformations, and then Q must be conserved, right? So which means that once I start building up physical states from the ground state, I must satisfy the level matching condition. So it's not the same. See, your point with momentum is very different because we build up our Fock space states as eigenstates of the momentum operator. So we built our Fock space states as the eigenstates of the Hamiltonian.
But we're still free to choose our initial condition with different n.
Okay, so what I missed a little bit is that I assumed that, it's clear that it will go exactly the same way how it will go in the orbit string. But I guess, so I already said that the ground state is given by that expression. Right? So we denote the ground state this way. And so this is, it's defined, we define the ground state in the following way. So this is the class times, and then I have a piece of I, the low center of mass, case of I. And then I'm requiring that for all loading vanishes, and it's positive, and it's the same. And then I can construct a general state, and the general state is constructed again by acting with raising operators. So the general state will have n and tilde k plus I, and it's going to be equal to product I of 1 to p minus 2. Product I equals 1 to infinity, alpha minus n I, and I equal n, alpha minus I tilde, and tilde I n. So the only difference now is that I have to act with that right oscillators, and so then I have n and tilde to the power n. And those are just from different normalizations, and then I have L'Oreal expressions. I have active on 0, 0. Right. And so then, so that's the way how I construct my Fock states, right? So so Q acted on a vacuum annihilates the vacuum by explicit construction of the operator, right? And then Q quantity is conserved. That's another way to. So I guess that was an important point that you raised. Q is conserved, which means that once I construct these physical states, because Q is conserved as my string evolves in a lifetime time, right? Which means that it must have the same quantity. Okay, so there will be various processes in my string, so there can be exchange between various excitations on the string once I start interacting. But whatever is happening, that capital Q must be conserved, which tells me that n must be equal to n squared.
I think there was a question that asked.
Yeah, sorry. Hey guys, question.
Yeah, I was just wondering why.
You can do the same. Yeah, you can do this. I just choose to construct sort of an explicit expression and as an operator acting on my Hilbert's.
Okay.
All right, guys. So what did I say? Right. So let's go back and discuss the spectrum. So we have this mass on-shot condition with level matching. So again, let's look at level 0. So at level 0, so I'm not exciting any oscillator. So we'll look at the ground state. So n equals n equals to 0. So in this case, m squared is going to be equal to 2 minus d divided by 6 alpha prime. And very much like in the open string case, this guy is a tachyon. Yeah, it's a tachyon provided when d is larger than 2. And as before, this tachyon we shouldn't worry about. We get rid of it once we impose supersymmetry. So we have to look at level 1, okay, first level. And so here the level matching condition becomes important because in the open string, what we could have taken that we just act with a single raising operator. So in the case of the closed string theory, that is not possible because that would violate level matching condition. And so in fact, what we have to do, we have the first excited state, which corresponds when we excite the level 1 oscillator on the left and on the right. And so the explicit expression for that is alpha minus 1 acted on I, j minus 1, and then 0, 0, k. Right? So those are the states at the next level. And so these states have mass, m squared. And so the m squared here is 26 minus d divided by 6 alpha prime. Okay, so all I have to do here, substitute n equals 1 and tilde equals 1, and you get this formula. So again, the arguments are as before. We want to ask the question. So here, now we have, one is the left moving, the other one is the right moving excitation. And so here we have an object which transforms as rank 2 tensor under Lorentz transformations. And so the number of states that we have here is d minus 2 times d minus 2. And we want to ask, so first of all, we'll figure out that there is no irreducible representation of this dimension, but there is a reducible representation. There exists reducible representation in S of d minus 2, right? So when the little group is S of d minus 2, then we can construct a sum of irreducible representation, which will have d minus 2 times d minus 2 states. So because the little group is S of d minus 2, so those states must be massless. So that tells us that the critical dimension is again 26. So the critical dimension of the closed string is exactly the same as in the open string. Now, this is irreducible representation, and sorry, this is a reducible representation. And what we can do, we can actually make it into an irreducible representation. So let me do it. So this is an object that carries two indices. And so I can break it into a symmetric traceless part. I plus, sorry, minus 2, ID minus 2, delta j. Okay. So this is a symmetric traceless part. Then there will be an anti-symmetric part, which is ij minus ji, and then plus a trace. Okay. So now all the terms here, so this is symmetric traceless, sim traceless, this is anti-symmetric, and this is trace. And so now all these pieces transform in irreducible representation of S/D minus 2. Okay? So what you see here, is that in the spectrum we have a symmetric traceless representation, a massless state, which transforms a symmetric traceless representation of Lorentz group, and that's our gravity. Okay. So those excitations correspond to a gravity. Again, we study perturbative excitations, right? So those will be the graviton which propagate over the background of Minkowski spacetime. Okay. And I can repeat exactly the same words. As with open strings. So once you have this massless vector boson there, that lead to a gauge symmetry. So here you have a graviton, and once the interactions are being turned on, you will naturally get the Einstein gravity. So you will get an interaction described by Einstein-Hilbert term plus additional corrections. All right, guys. So let me recap. Can I have 10 minutes from now?
How about anti-symmetric interest?
Sorry?
How about anti-symmetric part?
Yeah, so I'm going to recap this. So I'm just going to tell you what are the massless states in general. Yes, just 1 second. But can I have 10 minutes? Depends on if I have or not. What I'm going to see. I think. Okay, good. So right. So good. So what we see that there are open and closed strings. There is a tachyon always in the bosonic string, and then there are massless states. And past this level 2 states are always massive, right? Because all these higher level states will have higher mass, right? So the mass can go only up as you increase the level, and so those states are massive. So if I ask the question, so much like we do in quantum field theory, can you write down the interactions between the like states? So this is kind of the perspective of low energy effective theory. So if we assume that we can do only low energy experiments, if we assume that our experiments are lower energy, so meaning that we do not excite massive string modes. What this means explicitly, so 1 over alpha prime, 1 over root alpha prime, which is the same as 1 over length of the string. So that's a characteristic energy scale in the string theory. So this energy scale is much, much larger than energy scale available in our experiments. So then the only states that we will see are massless states. Massless states. So there are tachyons, but I'm telling you that the tachyons will be removed from the spectrum, and I will. The reason I asked for 10 minutes and you gave me 15. So I will explain you exactly the way how some states can be removed in the spectrum. So now what you will have massless states, and so let's recall what kind of massless states we have. So in open string case, so the massless states, the massless state that we had was just a boson, vector boson, A mu, and then in the closed string state, so what we have a graviton, G mu nil, which is a massless traceless fluctuation, and then what you asked that besides graviton there is an additional field. So that field is B mu nu, so that's an antisymmetric massless field. And then on top of that, there is a scalar, right? So when we did this decomposition into irreducible representation, the last piece was a trace, and that trace is a singlet, is in a singlet, so we have a massless singlet. So those are the states of the closed string. And so the point is what will happen. For now, if I'm going to ask the question, what is the field theory that will describe the interactions? Well, I would have to write down Maxwell Lagrangian in 46 dimensions, and I would have to write down perturbative Einstein-Hilbert term again in 26 dimensions plus 3 two-form field, right? So this is an antisymmetric field. B mu nu. So this is kind of a generalization of abelian fields, right? So if I have A, the corresponding field strength will be the exterior will be dA. So this is the field strength corresponding to a one-form gauge potential. So this is one of the propagating massless forms, and so there will be once we turn on interactions, there will be a gauge symmetry associated with this. So there will be a gauge symmetry. So here the gauge symmetry is x mu goes to a mu goes to a mu plus del a mu, and or in the level of the form, a goes a plus d psi, where psi is the gauge. So here there is, I have B mu nu, and so once I turn on the interactions, it will get promoted into a new kind of gauge symmetry, and so that will be a gauge symmetry when my B will go to B plus dA, where A is some vector, one form. Okay? And so there will be a field strength associated, the three-form field strengths associated with massless field B, which is dB. Okay. I'm sorry, it's a bit incoherent what I'm saying here. So I think what I'm trying to say is that there are these massless degrees of freedom, right? There are these massless degrees of freedom. And in order to get rid of the tachyon, you also have to include the supersymmetry. So it turns out that the series that describes the interactions of these fields plus the supersymmetric partners is what is called the supergravity. Okay, so a supergravity is a field theory describing the like massless excitations of the string. And so what we discovered with you today, we discovered the spectrum of supergravity, the spectrum of bosonic spectrum of supergravities that come from string theory. So, good. So now, finally, any questions so far? Okay. No. So, one last thing that I want to discuss, and then we will go back here. There will be slight refinements of the specifications, and you will find out that in fact there are different supergravities. And then we will talk what are possible topically consistent string series are out there. So what I want to talk about, I want to talk about unoriented strings. Right? And so here you will see how imposing additional symmetry leads to a projection of certain states in the spectrum of the series. So remember when we talk about open string, so we always had two ends, and we said that one end is L. So one end is corresponding to sigma equals 0, and the other end corresponding to sigma equals L. So in fact, what we talked about, everything that we talked before was when there was a natural arrow from one end to another end on the string. And so similarly for the closed strings, right? For the closed strings, even though we didn't, there was a freedom, where do we fix an origin on a closed string, there was still a certain direction in which our sigma coordinate acted. And so, so those examples that we discussed corresponded to oriented open plus closed strings. However, if you think about string as a geometrical object, you might notice that, well, in fact, this is your choice. This is your choice to choose orientation. But what if I don't want to? For example, what if I don't want to say which end sigma equals 0, sigma equals L? Or what if I don't want to choose orientation on a closed loop of the string? And so, in other words, what you're going to talk, you can say that you can make unoriented strings by imposing the following symmetry. So, unoriented strings. So a natural way to do is, in some sense, what you want to say is that you're going to identify those ends of the open string. It's still going to be an open string, but you insist that there is a symmetry. Sigma goes to sigma prime, L minus sigma, right? So whatever's there, if you, so this is a symmetry transformation both for open and closed string. So here you can see explicitly in the open strings, what the symmetry tells you is that it does not separate the left and right ends of the string. So this operation is called Wolfsheet parity. Wolfsheet parity. And so there is a generator omega corresponding to this Wolfsheet parity transformation, and pretty much the way how it acts. So it's an operator omega that acts on x sub I of tau and sigma on our Wolfsheet transverse scalar in such a way that it speeds up back the same field, same value of tau, but the value of sigma gets changed into L minus sigma. So notice that unoriented strings are in some sense special case, right? So you are putting an additional requirement. You are saying that I'm going to require that in the case of open strings, that is easiest to see, I'm not going to distinguish the ends of the string. And so that leads to the existence of this Wolfsheet parity. Now, if we do Fourier mode expansion, and we ask, how does this translate into Fourier mode expansion? And so what you will find out, that omega acting on Fourier coefficients those will be equation and manipulation operators, right? When we quantize it, corresponds to the following property. So this is in case of open string. Okay, so for the open strings, we will have our Fourier modes will pick up -1 to the n. This is very simple. All you have to do is just substitute the expansion here and here, and you will see that once sigma goes to L minus sigma, you're going to pick up -1. Now, in the case of closed strings, what's happened is that the parity operator will transform left and right movers. Okay? So it's going to go this way. Alright, and so this is a projection operator. The reason why that is a projection operator because it's close to 1 on our states. So now we want to ask the question. So once we have this parity operator, how do we construct states of unoriented strings, right? What we're going to do, we're going to assume that the vacuum of the string is invariant. So in other case, so let's look back at open strings, right? So we're going to make an assumption that our vacuum is invariant under this parity transformation. So let's go back to it, and it has parity plus. And in case of closed strings, I have omega that is 0 to k. Again, with plus. So now, if I ask how does my parity operator act on the excited states of the string, so I have omega active and comma k, and so you can see that that there will be a factor of -1 to the little n, and so if you act with a whole bunch of raising operators, you'll figure out that what you have here is a factor -1 to the n, n comma k, and so in this case, omega acted on n tilde k is going to be equal to n tilde n comma k. So in case of open strings, you will get a factor -1 to the n, where it is the total level. And in the case of closed strings, what you have just the exchange of left and right moves. Okay, so now if we talk about unoriented strings, so the physical states of unoriented string must be invariant under this omega transformation. It's similar to our operator Q discussion. So omega acting on the physical states must do nothing. Okay, so our states must be invariant, so the difference is that here the eigenvalues are plus or -1, so it's not annihilated. And so you can see that in open unoriented strings, A mu is projected out. Right. So now, if I ask that my spectrum is invariant under certain symmetry, in this case it will be Walsh parity invariance, I remove a massless vector boson from my theory, and the reason for that is because in order to produce this massless vector, I need to act with a single oscillator, and a single oscillator will give you -1 here when they act as a carrier transformation. So similarly, you can see when you talk about closed unoriented strings, closed unoriented strings. So here you have the states of your string must be invariant under exchange of left and right movers. So if you go back, so this is a state that was a graviton. So the graviton was asymmetric traceless excitation, and this guy was traced. So those two guys will survive. But the BU field will get projected, and the reason why it'll get projected because one of the indices come from the left movers, and the other index comes from the right movers, and the field itself is in the anti-symmetric representation. So BU is projected out. Okay. So now finally, let me make some conclusive remarks. So when we talk about string theory, we would have to combine open and closed strings. So what are the consistent theories? Meaning that those theories are well defined perturbatively, and perturbatively they don't know about each other. So consistent perturbative string series. So let me just say, so closed oriented, so massless fields are again B mu and phi. Okay, so in the dilaton, then there is closed unoriented. So that's a well-defined series that stand on the stand alone. So this is G mu and phi. Then it turns out that it doesn't make sense to talk about open strings. So it makes sense to talk about open strings when there are no interactions. But when there are interactions, the ends of the open string can get together. And so the open string will contain, is inconsistent in itself. You must include also closed strings as well. And when we get to the computational scattering amplitudes, we will see this explicitly. So in other words, once we talk about open string, we must compute also closed strings. And so we have another pair of possible string series, open plus closed oriented. So this is the theory that has Einstein gravity, some two-form gauge symmetry, and dilaton plus vector field, and then they can be closed plus open unoriented. Okay. So this theory has this G mu plus phi at the massless level, and then of course there is infinite set of massive levels. So, so what we have to conclude is that inconsistent string series, there will always be a gravity, right? So there is always a graviton, right? And so also what we conclude that there is always a tachyon, and the tachyon can never be projected out by the discussions we do here. All right, guys. So you know the homework, which is due in 2 weeks, and so next lecture, we don't have next lecture. We'll meet in 2 weeks, and we'll start talking about conformal field series. Yes.